In this video, I'm going to be talking about homework 4, specifically question number 7.10. And that question is, suppose a line L contains a point D that is on the inside of triangle ABC. And then we need to show that L must meet at least one of the sides of the triangle. So what that says is that we have triangle ABC, and D is a point on the inside. And what we're trying to prove is that there's some line L that has to go through at least one of these sides. Okay, so we're given D is on the interior of triangle ABC and D is on some point L, or some line L. Right? We don't know much about that line. We just know that D is on some line L. Okay. Now to make this maybe a little bit more interesting, not interesting, but a little bit more clear, by I2, L must contain at least 2 points. So point D is one of those points, which means that there has to be another point, which we're going to call E. Okay, and that'll help us out in a little bit. So we need to prove that there exists a point E prime that's on L intersect AB, that's on L intersect BC, or that's on L intersect AC. So we just have to prove that one of these things is true. So there are 3 ways that I kind of split this up into 3 ways. There are 3 ways that this can happen. Either E, our point E prime, I guess I'll just call this E. E is a point on the triangle, E is a point on the outside of the triangle, or E is a point on the interior of the triangle. And actually, I'm going to leave this as E prime. Okay, so again, 3 different cases. And in order to prove that, we're going to be using a lot of proposition 7.2, which is plane separation. And what that says is if L is a line, then the set of points not lying on that line can be divided into 2 non-empty subsets, S1 and S2. And there's 2 cases for that. 2 points A, B not on L belong to the same set. So A is related to B if and only if A, B does not intersect L. Right? So if we have L and we have AB, right, this segment does not intersect L, so they're on the same side. And then on the other case, 2 points AC not on L belong to the opposite sets, so A is not related to C if and only if AC intersects L in a point. Right, so we're going to put C on the opposite side of L. These 2 things are on the opposite side if and only if AC intersects 1 point on L. Okay, so we're going to be using that a little bit, especially in case 2 and 3. The first case is really easy. So we're going to set E prime. E prime is going to be equal to E. That's just what we're going to be trying to do, right? So if we let E be a point on L and also a point on any of AB, BC, or AC, right? So I have this drawn here, right? E is either on BC, AC, or AB. Then either one of these 3 things can happen, right? So on the left on AB, if E is on AB, AB intersect L is just E, right? If E is on BC, then BC intersect L is just E, so that'd be this one over here. And then if AC intersect L is just E, then we have this right here, right? So this is the trivial case, so not a whole lot to explain. If E is on any sides of the triangle, then the line DE, or the line L, right, so each of these are potentially L, intersects one of the sides at one point. So in this case, E is E prime. So that's case 1. Case 2 is a little bit trickier because it's not as direct, right? So let E be on L and now on the exterior of triangle ABC, so we have one of these 3 cases drawn. Then one of AB, BC, or AC separate the plane by prop 7.1, plane separation. I think this should be a 7. No, this is 7.1. Such that E and D are on opposite sides of AB, BC, or AC. Then by the same proposition, L intersects at least one of the sides of triangle ABC. So what this means, we are we have a point E somewhere on the exterior of triangle ABC. So let's focus on this case right here. I'll delete everything else. All right, so we have point D. By I2, there must be another point. We have D on L. By I2, there must be another point on L, which we're going to call E. And we're going to set that on the outside of triangle ABC. Okay, now, E is on the outside. And AB, right, this segment AB is going to separate the plane into two subsets. E and D are on opposite sides of that line. And by Prop 7.1, that means that ED, or line L, must intersect AB at least one point. And this point would be E prime. And we could do this for any of the other conditions, right? It could go this way, it could go this way. If it intersects at a vertex, it's still part of one of the sides, at least one of the sides. In this case, it's just part of two. Okay, so that's case 2. Point E is on the exterior, which means one of those sides of the triangles cuts the plane into two, such that E and D are on opposite sides. And by Prop 7.1, that line L must intersect one of those sides at least once. Case 3, this is probably the most interesting case. So let E be on L, and that's going to be another point on the interior of triangle ABC that's not point D. Okay, so down here I have this drawn. Right, we have point D, which is given to us automatically. And now we have point E, which is on the interior of triangle ABC. By Prop 7.2, which is the plane separation, L separates the plane into two subsets, right? So if we draw this line L through ED, that's going to separate the triangle, the plane, into two subsets. And the idea here is that L splits triangle ABC into two subsets, so then the two of the vertices of triangle ABC must be on one side and one must be on the other, right? So it's going to at least split two vertices into two different sides. So either AB is related to B, A is related to B, and B is not related to C, and A is not related to C, which means that A and B are on the same side. And then the same for the other two, right? So either A is related to B, so A and B are on the same side. A is related to C, so A and C are on the same side. And C is not related to B, and A is not related to B. Or C is related to B, and C is not related to A, or B is not related to A. Okay, so again, if we have three vertices and we split that into two, then there must be two vertices on opposite sides. And then we kind of use this, we kind of do the same thing we did above. There must be two opposite points, or there must be 2 points on opposite sides of L. And then by 7.2, L must intersect one of the sides of triangle ABC. So I have an example drawn here, and I'm going to use this to explain, and everything else is going to be the exact same. It's just rotated L differently, or naming vertices differently, right? So we have point D, which is given. E is now on the interior, and the line through ED is called L, right? So in this case, it splits the entire plane into two subsets. In this case, A and C are related to one another. B and C are on opposite sides. And A and B are on opposite sides. So because B and C are on opposite sides, there must be a point on L through BC that intersects it. Right, L splits it into two, so the line segment BC must intersect L at one point. And we could do this the same way for either of these other two conditions. And you should note, and I was thinking about this a little bit earlier, if ED goes through a vertex, the same is going to be true. And we can just focus on the side that splits the segment into two, right? So if ED, if the line L through ED went through a vertex, right? We would just focus on this point right here. So the same is still true. B and C would be on opposite sides. Therefore, the line L must intersect the segment BC at least one point. Okay. So these two cases really rely on proposition 7.2, that plane separation proposition. And then case 1 is really, really trivial. But that is my idea of how to do 7.10. And thank you for watching.